Hello again, students. So, in this video, we will step away from balancing chemical reactions to look at the voltaic cells. So how do we take these redox reactions and harness them for energy? How do essentially batteries work? And so that's where we're going to focus on, and we'll eventually relate this back into our friend Gibbs and equilibrium constant once more. Let's go ahead and get started. So, the idea is, well, what we work these redox reactions by creating batteries. We create what's called a voltaic cells by putting these two half reactions together in such a way that we have a wire across them. The cell potential creates a voltage that the electrons essentially work like the same way as a water wheel, at least in practicality, that essentially we can create some sort of energy the electrons want to get from one side to the other. And so because they're moving forward, they're going to push this, you're going to have to push through this wire to get from one place to the other. And then we're going to apply some sort of motor to that, and it's going to, as the electrons pass through, we're going to essentially capture this electron motion as work. I know that's kind of a roundabout, weird way of saying it, but the idea is that the electrons want to go from point A to point B, and if we put something for them to essentially have to push through, we're going to get some work, just the same way as water wants to run downstream, and if we put a wheel in the way, it's got to turn that wheel to get past. And so we create work in that way. So these cells are called voltaic cells after Alessandro Volta, sometimes called galvanic cells after Luigi Galvani. So early electrochemistry pioneers, basically, who created these cells capable of doing work. Now, they consist of essentially two individual half-reaction cells containing some sort of conducting fluid and some electrode capable of conducting electricity between the two. They need to be connected both by a salt bridge from solution to solution, and they need that wire that connects the two electrodes, which we can use to draw energy off. But the one half cell is the reduction, the other is the oxidation. So the electrons will flow. Electrons are going to flee one reaction, flee the oxidation. And they want to flow towards the reduction. And so they're going to go there, and because they want to go to the reduction side, we're going to be able to capture that energy. But if you're missing any one part of this battery, it's not going to work. If you don't have the conducting solutions good, you're not going to be able to capture any energy. If you're missing an electrode or the wire is broken at some place, it's not going to work. If you're missing a salt bridge, the reaction's not going to work. I found that out the hard way. We're making miniature little conducting probes, and if you get air stuck in there in a certain way, that you essentially break the contact between the salt bridge and the fluid and the electrode, you're not going to get a battery that works. Now, we're going to separate these two half cells into what we call the anode and the cathode. Anode being negative, cathode being positive, and basically, the one way to think of this is the oxidation occurs at the anode. The oxidation occurs at the anode, so the negative side shoots off the electrons, and the electron wants to flee from the negative. Electron, negative, and negative want to repel each other. So the anode produces electrons, and they flee to the other side, which is the cathode. The cathode of reduction occurs. So the electrons are trying to fling themselves toward the positive side. And so this is where the electron is going to combine with a solution of metal, which is going to deposit itself on the electrode. Ideally, the electrode will be made up of the same component as your solution, so we don't risk covering it up with a non-conducting product. Now, because we have negatives going to one side, and so one side we have, like, say in this case, zinc dissolving, so we're getting positive 2 ions suddenly appearing in solution, so it's getting more positive in solution. The other side, copper 2 plus, is leaving solution because it's being deposited as copper 0. So one side the solution is becoming more positive, the other side the solution is becoming less positive. The salt bridge is there to deposit cations and anions from the salt to balance the solution. So as more zinc dissolves into the one side, nitrates are leaching from the salt bridge into solution to balance things out. As copper is leaving solution, some potassiums are leaching from the salt bridge into solution to balance out the loss of positive charge, so that both solutions stay neutral charged. Now, the voltaic and galvanic cells always occur in the spontaneous direction, so they always do work. By saying voltaic or galvanic cell, we are implying that this is a spontaneous reaction. So the entropy of the universe must be increasing. These reactions are always written, regardless of what type of battery we're working with. They are always written anode first. Here's the weird thing and the annoying thing. If several reactions are possible, the largest voltage reaction will always occur. If you have more than just one type of ion in solution, the one that creates the largest voltage will always occur. So if you have an unfavorable reaction in solution, you might accidentally do stuff like, say, split water into hydrogen and oxygen, which can create a bomb. So we always want to, that's why we use, for example, nitrate, which doesn't really want to be oxidized any further, and potassium, which really doesn't want to be reduced. So that the salt bridge remains largely unreactive. But if you have something that doesn't want to be oxidized or doesn't want to be reduced, it won't. These guys are always spontaneous. So the more spontaneous the reaction, the more likely it's going to occur. So one way to write this without drawing out a picture each time is this shorthand symbology. We will use long bars to symbolize a break between essentially solutions and a double line to separate the half cells. So we have the breaks essentially symbolize we're going from solid to liquid or solid to gas or something like that, and the double bars separating the two cells. So writing anode first, you essentially drawing this. So zinc with a line. And in solution, we have 1 molar zinc 2 plus. And we have the double line to separate the half cell. And so writing from left to right, copper 2 plus, and single line goes to copper solid. All components of both half cells will be described, including their concentrations. The only thing that is not included is the salt bridge between the two. But like if there's more than one ion in solution that is important, we'll put them both. Occasionally there'll be a reaction that does not have an obvious electrode. Like if I'm going from iron 2 plus to iron 3 plus, or if I'm going from protons to hydrogen gas. In these situations, we would have to include a non-reactive conducting electrode such as platinum or carbon. So in this example where I've used fluorine and iron 2 plus goes to iron 3 plus and fluoride, the first cell is platinum, and we have 1 molar of iron 2 plus and 1 molar of iron 3 plus. Double bar, and so we'd have 1 atmosphere of fluorine gas bubbled into 1 molar fluoride solution with a single bar platinum electrode that helps conduct the cell potential of these two half reactions. So sometimes we'll use platinum electrodes. Platinum doesn't really want to be oxidized or reduced, so it remains largely unreactive and doesn't work. Now, when we calculate the energy, we're going to calculate the voltaic cells as electromotive force. We measure this electromotive force as a cell potential. So we say E of the cell. And this is done in units of volts. A volt is a fancy way of saying joules per coulomb. Joules per electronic charge. So how many energy per electron that runs through the giant water wheel of work. Now, we can calculate these under standard or non-standard conditions. We'll get to non-standard conditions later, but standard conditions are 1 molar, 1 atmosphere, and 25 degrees C. But to calculate the E cell of the redox reaction, now pay close attention. This is the easiest thing we'll do. You have to do it right, but it's the easiest thing. It's the one time we do not care a whit about the coefficients. We will simply look up the cell potentials from a table and subtract the two. Specifically, we will subtract the reduction, since the cell potentials are always written as reduction cell potentials. So we're going to subtract the oxidation cell potential from the reduction cell potential. So the oxidation will be appearing opposite to how it appears on the table. So by flipping the reaction, we're flipping the sign. So that's why it's being subtracted. The reduction cell potential, which happens at the cathode, will appear identical to how it is on the table. It might have a larger coefficient, but it will have the same ratio of products and reactants. It might have 3 of all the things, but it will have the same ratio. So you're taking essentially the left side, the anode, and we're subtracting that from the right side, the cathode. Once again, there is no such thing as an absolute reduction potential. Just like there's no absolute Gibbs and no absolute enthalpy. We have to measure this from an artificial reference point, because you can't have an oxidation without a reduction. So where do you call 0? And so we take the simplest reaction that we can and call that 0. You can't have an oxidation without a reduction. So we say if hydrogen, the standard hydrogen electrode, our middle point of all of our reactions, hydrogen being reduced to hydrogen gas, protons being reduced to hydrogen gas, if we say that is 0, then we can measure all cell potentials off of that. So protons go into hydrogen gas, and we measure chlorine, we can get chlorine cell potential. Then we can use chlorine to measure a whole bunch of other cations and go back and forth until we fill out the entire table. But we have to set an artificial 0, and that is our standard hydrogen electrode. So let's look at this. I cannot easily get to my .chem and still do this, so we'll just work from here, but it is easily enough. So our standard reduction potential table. You'd be given something like this if you ever needed it on the test. But cell potential tables are traditionally given as a reduction reactions and as reduction potentials. Now, depending on the table, it could be in order of alphabetically, or they could be in order of cell potential with reference to hydrogen. So in this case, we can look at here like, oh, hey, it's going down in cell potential and eventually gets to 0 and then goes negative because it's less likely to be reduced than hydrogen is. Now, please note, because a voltage is a joule per coulomb, this is the one time our coefficients do not matter. So just because we say 2 gold, 3 plus, and 3 hydrogen goes to 2 gold and 6 protons, we look, oh, gold 3 plus, 3 electrons goes to gold. Do I need to double this number, 1.5, to get 2 gold 3 plus? No, we leave it as 1.5. Since hydrogen is in reversed, so we have H2 on the right instead of H2 on the left, we reverse that. We're going to subtract that, but it's 0. We don't need to multiply it by 3, even though 3 times 0 is still 0. We don't need to multiply. So the cell potential of this reaction is just 1.5 volts. 1.5 volts. A positive cell potential is spontaneous. So this would produce 1.5 volts of electricity, and it would produce work. I will not be able to easily go to the document camera and still have the cell potential up, so I'm going to just try to highlight as best I can. So cobalt 3 plus goes to cobalt 2 plus. 3 plus to 2 plus has 1.82. Let's look for silver. That's based on charge. Here's silver down here. We notice silver 1 plus and silver solid. This is in reverse, and that is 0.8. So 1.82 minus 0.8 is 102. Let's look at chlorine and chloride. Chlorine and chloride. Chlorine right here goes to 2Cl minus. That's 1.36. Then we have hydroxide goes to oxygen and water. So we need oxygen and water and on one side and hydroxide on the other. So you might have some that are similar but not quite. This is oxygen and protons go to water. Not quite what I want. There's oxygen and protons go to hydrogen peroxide. Not quite what I want. Here we go. Oxygen plus water goes to 4 hydroxides. 0.4. So we have over here 1.36 minus 0.4 would be, well, 0.96. So still spontaneous. We have copper plus 1 goes to copper solid. That's at 0.52. We have F minus goes to F2. Okay. So this is the first case of this is not going to be spontaneous. But if you have a chemical reaction written, do it as written. Don't choose the most positive number. Do it as written. So 0.52 is my reduction. 2.87 is my oxidation. So 0.52 minus 2.87 is going to give me negative 2.35. So this is non-spontaneous. This would not occur. You could make it occur by putting work in, but it is not easy. We have hydrogen peroxide. Hydrogen peroxide goes to what? We got to figure this out. But let's figure out the chromium first. Chromium 3 plus goes to dichromate. Let's see where we can find. There's dichromate and chromium 3 plus. So notice there's 7 waters missing, and the chromium side, and 14 hydrogens on the other side. So it's probably going to be hydrogens. So we're missing 6 water. 6 of the waters have canceled out. So, but this guy is the reverse 1.33. Our hydrogen peroxide Here's hydrogen peroxide plus protons goes to water. So hydrogen peroxide must have canceled out some of these protons. The waters must have canceled out some of these waters. So it's probably 1.78 minus 1.33, which is going to give us 0.45. So that one's a little hidden, a little bit more difficult. But how many hydrogen peroxide reactions do we have? We have hydrogen peroxide plus acid goes to water. We have, let's scrolling down real quick. We have oxygen plus protons goes to hydrogen peroxide. That's not going to work. There's no oxygen in that equation. Let's see. Based on this table, there's no more hydrogen peroxide reactions. So that's really the only one that would fit with the available data. Now, with that in mind, the sign and the magnitude of our cell potential directly relates to our spontaneity and our Gibbs free energy. So whenever we have a positive cell potential, we have a spontaneous reaction. Now, a positive E would mean a negative G. So the reaction that relates the two is delta G is equal to negative NFE. Now, what this is essentially doing, we're introducing a new constant that will be given. Faraday's constant, which is 96485 coulombs per mole of electron. It can also be thought of as joules per volt mole of electron. But it is called Faraday's constant after Michael Faraday. The idea is that a volt is a joule per coulomb. So if I multiply a joule by Faraday's, I get a joule per coulomb by Faraday's, you get a joule per mole of electron. Then the N is a special definition for the moles of electron and not just simply the moles. We care about how many electrons get changed. This is where we can convert. If I had 6 electrons, N would be 6. 6 electrons lost and 6 electrons gained would be 6. 3 electrons lost and 3 electrons gained would be 3. Now, the way to actually calculate Faraday's is by taking the constant, which is a charge of electron, and multiplying it by Avogadro's number. But you don't need to know that. You'll just know that it's 96485, and you'll be given that number. So if I'm taking nickel and 2 silver plus goes to nickel 2 plus and 2 silver solid, it transfers 2 electrons. If the cell potential is 108 volts, so we're going to say 108 volts times 96485 times 2 moles of electrons, and that makes it negative, and then I have to divide by 1,000 to get from joules to kilojoules. But when I do that, I get still a very, very spontaneous reaction. Negative 208.4 kilojoules per mole. Very spontaneous. Now, the other thing we can do is, because we can relate delta G through K, we can directly relate E cell to K through a similar reaction. So we can set those two equations equal to each other and solve E cell. So a large positive E means a negative delta G, which needs a very large K. So rearranging, we get RT over NF ln K. R is 8.314. T is the temperature. F is 96485. And N is the moles of electrons. So taking our same 108 volts, if we plug in all of our values, you would get a K value, that is 3.39 times 10 to the positive 36. A very spontaneous reaction. So almost no silvers left, and no silver positives left, and all nickels converted. Okay, so for this problem, real quick, we'll talk about what would the delta G and K be for the following reaction. 2Na plus Cl2 goes to 2NaCl. And we have the half reactions, Na plus electron to Na, and that's negative 2.71. And Cl2 and 2 electrons, Cl minus, that's 1.359. Now, of course, that all depends on the source. But, okay, let's look at this. Step 1 is to find out our E cell. Our E cell would be, so this is reduced, this is being reduced, this is being oxidized. So our E cell would be 1.359 minus a negative 2.71. Relatively straightforward, relatively easy to do. 0.359 minus a negative 2.71, which would be essentially adding 2.71. 4069 volts. Yeah, that's a big voltage. Now, since this is doubled, 2 electrons lost, 2 electrons gained. Our delta G is going to be equal to negative NFE. Well, we got our E. We got 2 electrons, so our N is 2. Faraday's constant is 96485. We're going to divide all this by 1,000. Divide all this by 1,000 to get this into joules, but so negative 2, what did I say, 96.485 times 4069. Holy crapola, that has 785.2 kilojoules of spontaneity. This reaction is wicked spontaneous. And it's not too surprising. Our K, so E cell is equal to RTNF-lnK. You might see an alternate version of this equation where they turn the natural log into a logarithm by using a factor, and they factor out the R, the T, and the F because the temperature usually doesn't change much. And the only things left behind is the N. But why? Why do you need to? You don't need to. But so you can say NFE over RT is equal to lnK. Start with that. So our 4069 times 96485 times 2 divided by our 8.314 divided by, if this is done at 298. We have lnK is equal to 316.9. And if we try to inverse log this, we might actually have a problem. Yeah, it overflows. It overflows. Basically, if you have a factor that is over 10 to the 99th power, most calculators will not do it. And so what we get is actually an overflow error. So basically this is so spontaneous you can't easily measure it. Now there is ways to measure it. It's a pain in the butt, but you can measure it. So it's just e to the 316, but essentially it's 4.25 times 10 to the 137th power. So holy cow, that is spontaneous. So one more practice problem to leave us with this video. One more practice problem. What is the Gibbs based on this following reaction? What is the E cell based on this following reaction? If you have delta G is 632.17 and the reaction is 2 irons plus O2 plus 4H plus goes to 2 Fe2 plus and 2 water. We need to know the N. We need to figure out our N. So what is our N for this particular reaction? The easiest one is I'm going to break down the half reaction of iron and iron 2 plus. So 2 iron goes to 2 iron 2 plus. To balance this, you would need 4 electrons. So that means 4 electrons are going to be gained by oxygen because 4 electrons are lost by iron. So I know our N is 4. So delta G is equal to negative NFE. So that means we're going to take our delta G times 1,000 and then divided by negative NF. So with that in mind, negative 632.17 times 1,000. We're going to divide this by negative 2. Oh, sorry, negative 4. My bad. Negative 4. And divide this by 96485. And so we get the E cell. E cell would be 1.6. We'll say 4. 1.64. And that is the answer to this one. So we can turn G into E, E into G. We can turn E into K, or K into E. So keep in mind, we can play around with these. But that's where I'm going to leave you for this video. In the next video, we will look at E cell under non-standard conditions and how does that change. So that will be what we will look at next. And then we'll look at some real-world applications. But with that, this is Andrew signing off.